first quickly review the fundamental theorem of calculus. This says, if a function f is continuous on the closed interval from a to b, and capital F is an antiderivative of f, our function, on the closed interval from a to b, then the integral from a to b of our function f of x dx is equal to the antiderivative of our function f evaluated at x is equal to b minus the antiderivative of our function f evaluated at x is equal to a. So obviously, in order to be the fundamental theorem of calculus, this has to be pretty important, and it is. What this is saying is that you can calculate the exact area under a function on a given closed interval from a to b if you take the antiderivative of that function and plug in your upper limit of integration. Then subtract when you take the antiderivative of your function and plug in the lower limit of integration. That gives you the exact area under your function f on that given closed interval from a to b. Now let's talk about the second fundamental theorem of calculus. That says if a function f is continuous on an open interval I containing a, then for every x in the interval, d dx, or the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. Now the second fundamental theorem of calculus, much like the first fundamental theorem of calculus, is kind of a big deal. It's one of the fundamental theorems of calculus, and that's because it ties together two of the major concepts of calculus: differentiation and integration, derivatives and integrals. And what it says is that differentiation and integration are inverse operations, meaning they technically cancel one another out. So how this works is we are taking the integral of a function with respect to t. Now this variable in here, it doesn't matter what it is. We call it a dummy variable. It could be q, it could be r, it could be w. It doesn't matter. What matters is that this upper limit of integration here is a function with respect to x. So x has to be in our function here, because if x is not part of this upper limit of integration, then I can't take the derivative of this integral with respect to x. But since x is in our upper limit of integration, I can take the derivative with respect to x of this integral. And what happens is this upper limit of integration drops into our function for our dummy variable, and we get f of x. Again, this is important because it's showing you that differentiation and integration are inverse operations. They technically cancel one another out. Now you may be thinking, this still doesn't make sense. This is f of t, and when you take the derivative of that integral, it becomes f of x. Well, let's explain how this works. So to prove the second fundamental theorem of calculus, we're going to let f be continuous on the closed interval from a to b. And we're going to let capital F of x equal the integral from a to x of f of t dt, just like we said before. So if we know that capital F of x is equal to that definite integral, then what is the derivative of capital F of x? What is capital F prime of x? What is the derivative of this definite integral? In order to figure this out, what we're going to do is we're going to use the formal definition of the derivative. And if you remember, the formal definition of the derivative states if you want to take the derivative of a particular function, in this case capital F of x, we just need to evaluate the limit as delta x approaches 0 of capital F of x plus delta x minus capital F of x all over delta x. So now all we have to do to find our derivative here of this given function is evaluate each of these and then evaluate our limit. So capital F of x plus delta x, what is that equal to? Well, it's equal to this function, capital F of x, but instead of x, we're plugging in x plus delta x anywhere there's an x in this definite integral over here. So instead of our upper limit of integration being x, it's going to be x plus delta x. That's where this comes from. Then we're going to subtract capital F of x, which is just this function, this definite integral. So that's where this comes from, all over delta x. Now all I have to do is evaluate this limit to find my derivative here. So how do I evaluate this limit? Well, I have two definite integrals up here. And if you recall, definite integrals are just areas under the curve from x is equal to a to x is equal to x plus delta x, or x is equal to a to x is equal to x. So if I find those areas, I can just subtract them and then evaluate the limit, and I will find my derivative. So let's evaluate this definite integral first, the area under the function f of t from x is equal to a to x is equal to x plus delta x. Well, how do I find that? I'm not even given any x values. Well, that's where our graph comes into handy. So here is our function f of t, and we have a closed interval from x is equal to a to x is equal to b. So what we're going to do is we're going to look at this definite integral, which again is the area under the curve from x is equal to a to x is equal to x plus delta x. So where's x is equal equal to a, that would be this x value right here. Where's x is equal to x plus delta x? Oh, that's not on here. So what we're going to do on our graph is we're going to choose some x value on the interval from a to b to be x. Therefore, the y value of the function that corresponds with that x value is just f of x. Then what I'm going to do, because I need x plus delta x, I'm going to choose another x value, a certain distance away from x, and we'll call that distance delta x. Therefore, this new x value is going to be x plus delta x. And the y value of the function that corresponds with that x value is going to be f of x plus delta x. So now I look, and the integral from a to x plus delta x of this function is going to be the area under the curve from x is equal to a to x is equal to x plus delta x, this green area right here, this green region. Then I'm going to subtract the integral from a to x of f of t dt, which is the area under the curve from x is equal to a to x is equal to x in this case, which is this red region right here. So if I take the green region that we had and subtract out the red region, I'm just left with this region right here, which we're going to shade blue. This is what our numerator in this limit is going to be equal to. Now, because each of these are variables and we're not given an actual function, there's no way we can really evaluate these using the fundamental theorem of calculus. So what we're going to have to do instead is approximate the area of this blue region. So how would we approximate this? Well, it's kind of a rectangle, so we can use the area of a rectangle formula in order to approximate this region right here. Area of a rectangle is base times height. In this particular instance, our base would be delta x. The height, well, there's actually two different heights. There's f of x plus delta x, and there's f of x. So what we can do is, since we have just arbitrarily created an x and a delta x, we can make those whatever we want. So what we're going to do is we're going to shrink delta x. We're going to make it super small. And as delta x approaches 0, these two heights, these two y values, actually get closer and closer together. Meaning, as delta x approaches 0, f of x plus delta x is going to be equal to f of x. So I can approximate the area of this blue region as delta x approaches 0 as the base, delta x, times the height, which we said was f of x. Then what I can do is substitute this approximated area for this blue region for our numerator here, because we said this numerator of this given limit is actually equal to the area of this blue region, and we're approximating it with this value right here. So we can take that, plug it in here, and now we can evaluate our limit. These delta x's cancel each other out, and I have the limit as delta x approaches 0 of f of x. And since there is no delta x in this problem anymore, we just have f of x. So what just happened? Well, using the formal definition of the derivative, I evaluated the derivative of capital F of x, the integral from a to x of f of t dt. And I found that as delta x approaches 0, it's going to be equal to f of x. So I have found that the derivative of my antiderivative is equal to my original function. That's what I found. That's why the second fundamental theorem of calculus is so important. It's tying together differentiation and integration. Pretty cool.
I can carry up to 50 times my body weight. It's a tabletop.
Now, example 1 says evaluate, and we're taking the derivative of this definite integral right here. So the first thing that should go off in your head is, I'm taking the derivative of an integral. That means I'm going to use the second fundamental theorem of calculus, where differentiation and integration are inverse operations. They're going to cancel each other out. So the next thing you'll look at then are your limits of integration. Your lower limit of integration is a constant. That's good. Your upper limit of integration is a function in terms of x. Perfect. So all that's going to happen now, based on the second fundamental theorem of calculus, is that this is going to cancel out with this, and your x up here is going to drop in for your dummy variable. So you'll end up getting x plus 2. And that's it. Super easy. Part B, same thing. I'm taking the derivative of this definite integral. And the first thing that should go off in your head is, I'm taking the derivative of an integral. That means I'm going to use the second fundamental theorem of calculus, which says that differentiation and integration are inverse operations. They cancel each other out. The only difference here is my lower limit of integration is a function in terms of x, and my upper limit of integration this time is a constant, where they're supposed to be flipped. So how would I flip the limits of integration? Remember, I can always flip my limits of integration. The only thing I have to do is just put a negative sign out front of my integral. Now I have it correct in that my lower limit of integration is a constant and my upper limit of integration is a function in terms of x. So now I can take the derivative. But what about this negative? Well, technically it's just -1 times this integral. So if I'm taking the derivative of a constant multiplied to this integral right here, I can just take that negative, move it out front by the constant multiple rule, and now I can take the derivative like we were doing up here, where the derivative and the integral cancel each other out. The x just drops in for our dummy variable, which this time is w, and then I tack on that negative, and I get negative rad x to the 4th plus 1. And that's it.
What do you call an ant who skipped school? Truant! You try.
Okay, doing the same thing. Part A, we're taking the derivative of this definite integral. So the first thing that should go off in your head is, wait, I'm taking the derivative of an integral? That means I need to use the second fundamental theorem of calculus, which says that differentiation and integration are inverse operations. They're going to cancel each other out. And since here, my lower limit of integration is negative pi, that's just a constant. And my upper limit of integration is a function in terms of x. That means all I have to do is just cancel out the derivative and the integral and drop that x in for my dummy variable. So I get cosine of x. And I'm done. Super easy. For part B, I am again taking the derivative of a definite integral. And again, because I'm taking the derivative of an integral, I need to think about the second fundamental theorem of calculus, which says differentiation and integration are inverse operations. So these should cancel each other out. The only problem here is that in my lower limit of integration this time, I have a function in terms of x. And in my upper limit of integration, I have a constant. So what am I going to do? I'm just going to switch my limits of integration. And when I do that, I put a negative sign out front of my integral. Now I can take the derivative here. And what I want to do is, because I'm taking the derivative of a constant, -1, multiplied to this integral, I can just take that -1, move it out front of my derivative sign, and tack it on at the end. Now I'm taking the derivative of a definite integral, where there's a constant in the lower limit of integration, and there's a function in terms of x in my upper limit of integration. So I can just cancel these out, drop the x in for each of the dummy variables, which is q in this case, and then I tack on that negative, and I get negative secant x tan x. Now example 2 says find dy dx of the given function. We have our given function here, which is y is equal to a definite integral, the integral from 0 to 2x of cosine t dt. So this is just asking you to do the same thing we were doing in example 1, just in a slightly different way. So all we're doing is we're taking the derivative of this, meaning we're taking the derivative of a definite integral. The only difference here is that instead of having the lower limit of integration be a constant and the upper limit of integration just be x, in this case, our upper limit of integration is 2x. So what do we do when it's not just x? Well, what's going to happen is the derivative and the integral are still going to cancel each other out. This function in terms of x is still going to drop in for your dummy variable. But because you're taking the derivative and this is no longer just x, it's 2x, you're going to have to use the chain rule, meaning you're going to multiply whatever you get when you drop this in by the derivative of this upper limit of integration. So again, we're going to take the derivative of the integral. Those are inverse operations by the second fundamental theorem of calculus, so they cancel each other out. Because our lower limit of integration is a constant and our upper limit of integration is a function in terms of x, the 2x is just going to drop in, so you get cosine of 2x. But because it's not just x, you have to use the chain rule, so you're going to multiply by the derivative of 2x, which is 2. So you end up getting that dy dx, the derivative of this function, this definite integral, is going to be equal to 2 cosine of 2x.
What do you call an ant who sees into the future? Clairvoyant! You try!
Okay, doing the same thing. We're taking the derivative of this function here, and the function is y is equal to this definite integral, the integral from 0 to tan x of 4t squared plus 1 dt. So we're going to take the derivative, meaning we're going to get dy dx is equal to the derivative with respect to x of this definite integral. Now, notice, again, we have a definite integral where the lower limit of integration is a constant and the upper limit of integration is a function in terms of x. So perfect. These are going to cancel each other out by the second fundamental theorem of calculus, and we're going to drop our upper limit of integration in for our dummy variable t in here. So we're just going to get 4 tan squared x plus 1. But then, because our upper limit of integration is not just x, it's tan x, we have to use the chain rule, meaning we have to multiply by the derivative of tan x, our upper limit of integration. So we end up getting 4 tan squared x plus 1 times the derivative of tan x, which is secant squared x. And you're done. It's still pretty easy. All you're doing is just dropping in that upper limit of integration for your dummy variable and multiplying by the derivative of that upper limit of integration. Now example 3 says find dy dx of the given function. So we again have y is equal to a definite integral. The only difference this time is we now have a function in terms of x in our lower limit of integration and in our upper limit of integration. So what do we do when this happens? Well, I'm going to show you how to solve problems like this, and it's actually pretty easy. But first I'm going to show you why it works. So this is a definite integral, and to solve definite integrals, to evaluate definite integrals, we typically use the fundamental theorem of calculus, which says we need to take the antiderivative of our function. We plug in our upper limit of integration to our antiderivative, and then we're going to subtract when we plug in our lower limit of integration to our antiderivative. That is the fundamental theorem of calculus. But let's say, for example, we want to take the derivative of this, the fundamental theorem of calculus. What we would do is we would take the derivative of both sides of this equation. Over here, that's what this question is asking us to do. On this side, this is how we're going to evaluate it. So we're technically going to take the derivative with respect to x of each of these antiderivatives. Now, the only issue here is our lower and upper limit of integration are technically functions in terms of x. They're not constants like they normally are. So when I take the derivative of each of these, I technically have to use the chain rule, meaning I'm going to take the derivative of my outer function, which is just your antiderivative. So the derivative of your antiderivative is just your normal function, f. So it's going to be f of b times the derivative of b with respect to x, so db dx. Then over here, minus the derivative of your outer function, which is your antiderivative. So the derivative of your antiderivative is just your normal function, f of a, times the derivative of your inner function, which in this case is a, so it'd be dA dx. So what we have done is we have taken the derivative of a definite integral, which is exactly what we're trying to do here. And we now have this formula over here that we can use anytime you have a lower and upper limit of integration that are functions in terms of x. So let's use this in this example over here. We want to take the derivative of our function here, which is a definite integral, where the lower and upper limit of integrations are functions in terms of x. So when we take the derivative of an integral, we're going to use the second fundamental theorem of calculus, which tells us that these are inverse operations. So these are going to cancel each other out. Now, because the lower and upper limits of integration are functions in terms of x, each of them are going to require the chain rule, which is what this is saying over here. So when I take my derivative of this integral, I'm going to drop in my upper limit of integration to my dummy variable like I normally do. So it's going to be cosine of x squared. But then, because it's not just x, it's a function in terms of x, I have to multiply by the derivative of that upper limit of integration, by the derivative of cosine of x. Then I'm going to subtract when I plug in my lower limit of integration to my dummy variable for t. Then, because it's not just x, it's a function in terms of x, I have to multiply by the derivative of that function according to the chain rule. Now I just simplify. What is the derivative of cosine of x? That's negative sine of x. What's the derivative of sine x? That's cosine of x. Then I simplify this and I end up getting negative cosine squared x sine x minus sine squared x cosine squared x. That is the derivative of this definite integral up here.
Time for me to buzz off. You try.
Okay, doing the same thing here. I'm again taking the derivative of a function, and that function is a definite integral where the lower and upper limits of integration are both functions in terms of x. So when I take the derivative of this function, it's going to look something like this. Now, we notice we're taking the derivative of an integral, so based on the second fundamental theorem of calculus, these are inverse operations. They're going to cancel each other out. But in this case, like we said, our lower and upper limits of integration are functions in terms of x. Not only that, they're not just x. Down here we have negative x, up here we have x squared, meaning that each of these are going to require the chain rule when I take the derivative. So let's remember that formula we worked out earlier with the fundamental theorem of calculus. It looked like this. When we take the derivative of a definite integral where the lower and upper limits of integration are functions in terms of x, it's going to look something like this, where we have our function where we plug in our upper limit of integration and multiply that by the derivative of our upper limit of integration based on the chain rule. Then we subtract when we plug in our lower limit of integration to our function and multiply that by the derivative of our lower limit of integration based on the chain rule. So based on this formula that we have here, we're taking our upper limit of integration and we're going to plug it in for our dummy variable here. So it's going to be x squared to the third power. Then we're going to multiply that by the derivative of our upper limit of integration based on the chain rule. Then we have to subtract when we plug in our lower limit of integration to our function for that dummy variable. So we're going to plug in negative x for t here. Then we have to multiply that by the derivative of our lower limit of integration because of the chain rule. Now we simplify. X squared to the third power. We have power to a power. We multiply those together. We get x to the sixth times the derivative of x squared, which is just going to be 2x to the first, minus negative x, the quantity cubed. Anytime you have a negative number raised to an odd exponent, it's just going to stay negative. So that stays negative x cubed, times the derivative of negative x, which is just going to be negative 1. Now we simplify even further. X to the sixth times 2x to the first is going to be 2x to the seventh, minus negative x cubed is going to be plus x cubed, times negative 1 is going to be minus x cubed again. So there is our derivative of this definite integral. Now example 4 says write a function that has dy dx equal to secant x if y of negative 1 is equal to 4. So what this wants you to do is it wants you to create a function, y equals something, where the derivative of that function, the derivative of that something, is equal to secant x. So the derivative of y is equal to secant x. You're also given a point that needs to be included in that function, negative 1, 4. Now, this is more or less a trick question because it wants you to overthink it. It wants you to think about a trig function that if you took the derivative of it, you would get secant x. And there isn't one off the top of your head. So what you're going to do is you're going to outsmart them and you're going to say, okay, if the derivative of my function has to equal secant x, then I'm just going to make my function y is equal to the integral from some number to x of secant t dt. Because if I were to take the derivative of this, the derivative of the integral, those two things cancel each other out based on the second fundamental theorem of calculus. And since my lower limit of integration is a constant and my upper limit of integration is just x, the x would just drop in for my dummy variable and I would get secant x. That part of the question is satisfied. Now the only issue would be this point right here. How do I get -1, 4 to be a point in this given function? Well, a reminder, if you have a definite integral where the lower limit of integration and the upper limit of integration equal the same constant, that's going to equal 0. So what I'm going to do here to outsmart this question is I'm going to take -1 and make it my lower limit of integration. Now you say, why would you do that? Well, because if -1 is my a value, my lower limit of integration, then I could satisfy this part of the equation because if I were to plug in -1 for x, I would have the integral from -1 to 1 of secant t dt, which has to equal 0. So all I would have to do then to satisfy this part of the question is just add a 4 to the end of this function, making it y is equal to the integral from -1 to x of secant t dt plus 4. This is a function where if I were to take the derivative of it, I would first take the derivative of the integral and derivative of the integral, those two things cancel each other out and the x drops in for your dummy variable, giving you secant x. Then you take the derivative of 4, which is 0, so the derivative of this function does equal secant x. That part of the question is satisfied. Now for this part of the question, I would have to plug in -1 for x and get 4 out. So if I were to plug in -1 for x, I get the integral from -1 to 1, which causes this to equal 0. So 0 plus 4 does equal 4, meaning that both parts of this question are satisfied. So this function would be your answer to this particular question.